Welcome to Planet Pulse, where we explore the mysteries of the universe, the beauty of nature, the wonders beyond our Earth, and the questions that make us wonder, what's really out there? Picture this. It's a beautiful summer day back in 1950. A brilliant physicist named Enrico Fermi is having lunch with his colleagues. They're talking about all the amazing new things we were learning about space, stars, and the universe. The conversation turns to the possibility of alien life and flying saucers, which was honestly a pretty hot topic at the time. After listening for a bit, Fermi, known for his ability to ask simple yet profound questions, suddenly blurts out, "But where is everybody?" That simple three-word question has echoed through the halls of science ever since. It's the heart of what we now call the Fermi Paradox, and it's honestly one of the most fascinating and humbling questions we can ask. Enrico Fermi wasn't just any scientist. He was a Nobel Prize winner who helped build the world's first nuclear reactor. He was a master of what we call back-of-the-envelope calculations, where you can estimate a reasonable answer to a complex problem using just a few key facts and a bit of logic. When he asked "Where is everybody?" he wasn't just making small talk, he was actually doing a quick mental calculation. He considered the age of the universe, the sheer number of stars, and the time it would take for a civilization to develop interstellar travel. His calculations suggested that our galaxy should be teeming with life, and yet, we see nothing. No signals, no spaceships, no signs of anyone else out there. This question wasn't born out of fantasy or science fiction. It was born from a deep understanding of numbers and probability. Fermi realized that if life could arise on Earth, it could surely arise elsewhere. And if even a handful of those alien civilizations developed technology slightly more advanced than ours, they would have had billions of years to explore and colonize the galaxy. Think about it. Our galaxy, the Milky Way, has been around for over 13 billion years. Life on Earth has only been around for about 4 billion years, and we've only been sending radio signals into space for a little over a century. In the grand cosmic timeline, that's just a blink of an eye. So, Fermi's question forces us to confront a huge contradiction. On one hand, the numbers tell us that the universe should be full of life, maybe even intelligent life. On the other hand, our observations show us a silent, empty cosmos. This is the paradox. It's like walking into a gigantic, bustling city and finding all the buildings and streets completely empty. You know people should be there, but they aren't. It's an eerie silence that makes you wonder what's really going on, and it has sparked decades of debate among scientists, astronomers, and thinkers all over the world. The search for an answer takes us on a journey through astronomy, biology, and even philosophy. To truly grasp the power of Fermi's question, you have to understand the mind-boggling scale of our galaxy. The Milky Way, our cosmic home, is enormous. It's a spiral galaxy containing somewhere between 100 billion and 400 billion stars. That's not a typo. For every single person who has ever lived on Earth, there are dozens of stars in our galaxy alone. And that's just one galaxy. Astronomers now estimate there are about 2 trillion galaxies in the observable universe. The numbers are so large, they're almost impossible for our brains to comprehend. It's like trying to count every grain of sand on every beach on Earth, and then realizing that's just the start. Now let's think about planets. For a long time, we didn't know if other stars had planets like our Sun does, but thanks to amazing tools like the Kepler Space Telescope, we now know that planets are incredibly common. It seems that most stars have at least one planet orbiting them. Scientists estimate there could be tens of billions of planets in our galaxy that are Earth-like. This means they are rocky planets, roughly the size of Earth, and orbit their star in the habitable zone. This is the Goldilocks region, not too hot, not too cold, but just right for liquid water to exist on the surface. And as we know from our own planet where there's water, there's a chance for life. So, let's do some simple math. Just like Fermi might have, if we take even the most conservative estimates, say 100 billion stars in our galaxy, and assume that only a tiny fraction, maybe 1%, have Earth-like planets, that still leaves us with 1 billion planets that could potentially support life. 1 billion, and that's just in our own little corner of the universe. If life started on just a tiny fraction of those planets, say 0.1%, that would mean there are 1 million planets in our galaxy with life on them. it seems almost inevitable that some of that life would become intelligent, build civilizations, and start exploring the stars. This is where the paradox really starts to hit you. Our galaxy is ancient. It has been around for billions of years before our sun and Earth even formed. That means other civilizations could have gotten a head start of 1 billion years or more. Think about how much our own technology has changed in just 100 years. Now imagine a civilization with 1 million-year head start, or 1 billion-year head start. They would have had more than enough time to send probes, signals, or even colonists to every corner of the galaxy. Their presence should be obvious. Yet, when we point our telescopes to the sky, we find only a profound and unsettling silence. The Fermi Paradox can be summarized in a simple, powerful statement. Given the high probability of extraterrestrial life, why have we found no evidence of it? It's a clash between our expectations and our reality. We've been actively listening for signals from other civilizations for decades, through programs like SETI, the search for extraterrestrial intelligence. We use massive radio telescopes to scan the stars, hoping to catch a stray signal, a deliberate message, or any sign that someone else is out there. So far, all we've heard is the background hiss of the cosmos. No Hello Earth, no alien TV shows, nothing. One of the first and most straightforward ideas proposed to solve this paradox is what's known as the rare Earth hypothesis. This idea suggests that while simple life, like bacteria, might be common in the universe, the conditions needed for complex, intelligent life like us are incredibly rare. It's not just about being in the habitable zone. You might need a large moon like ours to stabilize the planet's tilt and create regular seasons. You might need a giant planet like Jupiter in your solar system to act as a cosmic vacuum cleaner, sucking up dangerous asteroids and comets. You might need plate tectonics, a magnetic field, and a very specific chemical composition. Maybe Earth won the cosmic lottery. The astronomer Donald Brownlee once used an analogy of an orchid to explain this. You can find weeds growing almost anywhere, under all sorts of harsh conditions. They're like simple microbial life, tough and adaptable. But an orchid is delicate. It needs the perfect temperature, the perfect humidity, the perfect soil, and the perfect amount of sunlight to grow. Complex life, the hypothesis goes, is like that orchid, the chain of events that led to our existence, from the formation of our solar system to the evolution of a brain that can ponder the universe, might be so astonishingly improbable that it has only happened once, right here. This idea is both humbling and a little bit lonely. It suggests that we might truly be alone, or at least that intelligent neighbors are so far away they might as well be in another universe. It paints a picture of a cosmos that is vast and largely sterile, with just a few precious oases of simple life, and perhaps only one world where beings have evolved to look up at the stars and wonder. If the rare Earth hypothesis is correct, it means our planet is not just our home, it's an unbelievably precious jewel in an otherwise empty cosmic ocean. It makes our responsibility to protect it even greater. If Earth isn't all that special, what are the other possibilities? One compelling idea is that intelligent civilizations are not rare, but they are short-lived. Think about our own history for a moment. We've only had the technology to communicate across space for about a century, and in that same time we've also developed the technology to destroy ourselves completely through, nuclear war or environmental collapse. Perhaps this is a common trap for any young, technologically advanced civilization. They discover science, create powerful tools, and then, before they can become a stable, spacefaring society, they self-destruct. The universe might be filled with the ruins of civilizations that burned out too quickly. Another fascinating and honestly, slightly spooky idea is known as the dark forest hypothesis. This theory comes from a science fiction novel, but it's based on some serious game theory. Imagine you are a lone hunter in a dark forest at night. You hear a rustle in the bushes. Is it another hunter, maybe a friendly face? Or is it a predator? You have no way of knowing. The safest thing to do is to stay silent and hidden. If you call out, you reveal your position to whatever else is out there, and you can't be sure of its intentions. In this scenario, the universe is the dark forest. Every civilization is a hunter. The logical, self-preserving thing to do is to hide. In this view, sending out signals like we do with our radio telescopes is incredibly naive and dangerous. It's like shouting, "Here I am," in a forest full of unknown predators. Maybe the reason the sky is so quiet is because all the other intelligent civilizations are smart enough to keep their heads down. This theory suggests that the silence we observe isn't an absence of life, but an indication of its intelligence and caution. Advanced civilizations may have learned from bitter experience that the only way to survive in a cosmic neighborhood is to remain unseen and unheard, observing quietly from the shadows. Then, there's the problem of technology and detection. We're looking for signals that are similar to our own, like radio waves. But what if a civilization that is, say, 1,000,000 years ahead of us has moved on to communication methods we can't even imagine? It might be like us, trying to find a modern Wi-Fi signal using a 19th century telegraph machine. Their communication could be based on neutrinos, gravity waves, or some other form of physics we haven't discovered yet. They could be broadcasting all around us, and we would be completely oblivious, deaf to their cosmic symphony because we don't have the right instruments to listen. This leads us to one of the most profound and honestly unsettling concepts related to the Fermi Paradox, the Great Filter. The idea, proposed by economist Robin Hanson, is that somewhere along the long evolutionary path from simple life to a galaxy-spanning civilization, there is a barrier, or filter, that is incredibly difficult to overcome. This filter could be one of many things. It could be the jump from non-living chemicals to the first living cell. It could be the leap from simple single-celled organisms to complex multicellular life. Or, more worryingly, the filter could be ahead of us. If the Great Filter is in our past, it's good news for humanity. It means that one of the steps we have already completed, like the origin of life, or the evolution of intelligence, is the incredibly rare event. It would mean that we are one of the very few, or perhaps the only species to have made it through. This would align with the rare Earth hypothesis, and would suggest that we have a clear shot at becoming a long-lasting spacefaring civilization. We would be the first ones to the party, with the whole galaxy laid out before us, waiting to be explored. It would be a huge responsibility but also an incredible opportunity. However, the scary possibility is that the Great Filter is still in our future. This would mean that life and even intelligence might be common, but something prevents those civilizations from surviving long enough to colonize the galaxy. This filter could be self-destruction through war, environmental collapse, or even a runaway artificial intelligence. If this is the case, then the silence in the sky is a warning. It's the silence of a cosmic graveyard, filled with civilizations that reached our current level of technology, but failed to pass the next great test. We might be approaching that same filter ourselves. And, well, we may be next in line. Ultimately, the Fermi Paradox is more than just a puzzle about aliens. It's a mirror that reflects our own hopes, fears, and our place in the universe. Asking, where is everybody? Forces us to ask, what does it mean to be human? And what is our future? Are we a rare and precious miracle, destined to bring life to a sterile cosmos? Or are we just another reckless teenager, playing with matches and destined to burn out before we ever grow up? We don't have the answer yet, but the search itself, the science, the curiosity, the wonder, is what makes us who we are. It drives us to learn, to explore, and to become better stewards of our own tiny, beautiful world.